All right, in 10.c, we're going to use the same prom scenario we used in the previous one. And so if you read the write-up, they changed the sample to 45 and 25 out of the 45 seniors go to prom, but I'm switching it back to the same scenario we had just to keep consistency on what we're doing here. So it was 70 seniors and 45 of those are going to prom. So moving on from there, do the data provide convincing evidence that a higher proportion of seniors are going to prom than juniors? So higher proportion is important as we write our hypothesis. So when I write my parameter, I want to indicate, okay, what is the difference here? P1 minus P2, it's the true difference in proportion of juniors and seniors going to prom. So, and I indicate which way I'm subtracting, juniors minus seniors. And in this statistic, I'm using the same p-hats we used in the confidence interval scenario, and we found that the difference of the two was a negative 0.08, right? Remember, P1 was 0.56 and P2 was 0.64. Now, when we write the hypothesis, notice it's P1 minus P2. The null is going to always equal 0. The alternative, it's always going to be the P1 minus P2 and the 0. Now, we need to indicate which correct inequality. That's where this statement comes in right here, higher proportion of seniors. Well, if seniors are higher and I subtract, that means that my result will be a negative number. So that's why I have less than. Now, it may make more sense to you to write your hypothesis like this, where P1 is equal to P2, and then the alternative is P1 is less than P2. And that's perfectly fine. Both are acceptable. Do the one that makes the most logical sense to you. So the name of our procedure when we do a hypothesis test is a two-proportion z-test. Hopefully that makes a little sense. When we do random, we check for two independent random samples, and this was stated. Independent meaning juniors and seniors don't overlap, right? And the 10% rule that we've checked before, we said 50 is less than 10% of juniors, 70 is less than 10% of seniors. Now when we get to large counts, things change ever so slightly. Instead of using P1 and P2, we now have to check large counts using a pooled proportion, all right, a pooled proportion. So what does that mean? Well, it's all because we make this assumption in our null that they are equal, right? So if they're equal, couldn't we just combine our samples and have a better indicator of the true proportion if they were equal of students that go to prom? So using that logic then, we pool them. So what do? We take the x value of the first sample, x value of the second, add them up, divide it by the total number of both samples. So when I do that in this example, I have 28 plus 45 over 50 plus 70 gives me this ratio, which results in a pooled p of 0.61. Now, this is where I'm going to use it in my large counts. So we talked about the pooled value when you add the x's and add the n's, and then you find that pooled proportion, right? This is the p number that we're going to use when you do large counts. It's only used when we do hypothesis tests with two proportions, kind of a special case thing. The reason we do it, anybody remember the reason we do it? Because we are making this assumption right here. We assume the null is true. If these two are really equal, why can't we just put them all together? Make a better sample, right? So because we make this assumption, we do this pooled p-value when we check our large counts. So so when I do my large counts, I'm going to do, let's see, the, what was it? The juniors was 50. So it's going to be 50 times 0.61. And then 50 times the complement of that of 0.39. So basically 31 is greater than 10. And so this comes out to like, 19? 19 is greater than 10. Okay, so that worked out. Now we're going to do the same thing with the other sample. The other sample was 70, so I'm going to just squeeze it in here. 70 times 0.61. So 43 is greater than or equal to 10. 70 times 0.39. So 27. And that's greater than or equal to 10. So they both pass the large counts. So this is where you're going to have to worry about the PC thing. Okay, this is the only place you're going to have to show me that work. This is where we use PC. Now, if you were having to write out the equation and all the stuff for standard deviation, this is the value you would use in your standard deviation formula as well. But since we're going to use the shortcut in our calculators, we don't have to do that. All right. So this is what you need to make sure you're showing. Again, this is a special case that only applies to two proportion hypothesis tests. Alrighty. So coming back, standard deviation. If you had to do it, you would use the pooled p-value. If we had to use it, okay. So the general formula for z. I'm not going to make you, the very, very general formula would be what? The statistic minus the parameter over the standard deviation, right? The really, really simple version of that. But the calculator is going to do the work for us. So in your calculator, what you need to write out, what you need to show me for work is a picture, okay? So let's draw our picture. What kind of test are we running? It is a left-tailed test, all right? And we said that if the difference of 0 is my center, what's the probability of getting this difference of negative 0.08? That was the value we were looking for. So what you need to show me on the work is like, we labeled 1 and 2. So x1, n1. This refers to the junior sample. So x1 of the juniors was 28. The n1 was 50. x2, n2. X2 was what, 45 out of 70? That's what I'm going to have to input in my calculator along with the inequality of our alternative. Then what you're going to produce for us is the test statistic, which is going to be z, and then the p-value. Okay? So I'll walk you through that. Okay, so we're going to go to stat, over to test. This is the two proportion z test. So look at number 6, right? So there's x1, n1, x2, n2. So we're going to go in and put in our values. Oops, I undid that, didn't I? So what was our first sample? 28 out of 50. And then it was 45 out of 70. Now, there it is. There it is. So look, it gives me the z-score. I can't see mine, but it's there. 9.1 or 9.2. Is that what y'all got? Yes. And the p-value is 0.18, basically. All right. So we'll go back to our paper. So now we know our z-score is negative 0.192, and our p-value is 0.18. Now we have enough to draw our conclusion. So we're going to say, this is a hypothesis. So since 0.18 is, greater than 0.05, we fail to reject the null. We do not have convincing evidence that, how did I phrase it? The true difference in proportions of juniors minus seniors is, what did we say? Less than 0. So we're just mimicking the alternative hypothesis here. All right? That gives you the general idea. Now let's try the back page. All right, let's try this. In the state step, this is just recapping what we're going to do here. All right, so we want to identify P1 minus P2. It's the true difference in proportions of whatever. And you put in your context. I guess I should zoom in a little bit for you. Okay, the true difference in proportions. And we said the null is always going to equal 0 unless you do the alternate form that I showed you, P1 minus P2. This could be greater than, less than, or not equal to 0, right? Depends on the question. So the name of our test is I would say proportion z-test, so you don't have to remember this P1 minus P2 thing. 2 proportion z-test, that's sufficient, and that's the way it's also named in your calculator. Keep it streamlined. Check conditions, and then notice this, we are using that PC thing for large counts. That's where you're going to have to show that, okay? So maybe we rewrite, what is PC? x1 plus x2 over n1 plus n2. All right. All right, in the do step, we're going to use our calculators very heavily on this. So we're going to write in x1, n1, x2, n2, and it will produce our z-score and our p-value. And obviously, we got to put the right inequality in our calculators. But as far as work for me, that's really all you have to show me. And then the conclusion is the same logic we've done all along. If the P is low, we reject the hoe. That's the same. All the same. All right. Ready to try another one? Sure. Okay. So here's the question. Do you sleep with a comfort object as a child, or did you? Do you still? No need to stuff that teddy bear from your infant years in your closet the next time you have a guest over. The odds are good that he or she has a comfort object too. A study conducted by Sleepopolis and OnePoll reported that 34% of adults still sleep with a stuffed animal, blanket, or other sentimental object, according to a survey of a random sample of 100 adults. All right. A similar study based on a random sample of 80 children said that 75% of children sleep with a comfort object. So then the question is asked, do these data provide convincing evidence that the proportion of adults who sleep with a comfort object is less than the proportion of children who sleep with a comfort object? All right, so let's do our state step. Maybe for you, the easiest thing is to start with the hypothesis and then define? I don't know. So let's think about this. So adult less than the proportion of children, right? So if I do the proportion of adults minus the proportion of children, the null is equal to 0. Now if adult is less than children, which inequality should I be using here? Greater than. Is everybody there? Like if this number's bigger, or if this number's less than this number, won't it come out negative? So this would be a less than. Is that okay? So when I define this, PA minus PC, I'm going to say the true difference in proportion of adults and children, proportions of adults and children who sleep with a comfort object. And if you make your subscripts logical, like A is for adult, C is for child, usually you don't have to like notate it, but if you get fancy and call it X and Y, then make sure you define what that is so the reader knows what you're doing. All right?
Wait, we stopped?
Yeah.
Like going back to the alternative,
Uh-huh.
like there's like less adults than like, so what, like if
Oh, it should be less than.
yeah.
Why did I put greater than? I think I was thinking less than, and thank you. It should be less than. You're right. It's Friday. Such a Friday, right? Okay, are we good with state? Yeah? No? What? Yeah? Okay. All right, let's plan this puppy. All right, what's the name of the test we're going to use? Two proportion z-test. Yep. All right, now let's check our conditions. Random. Do I have two independent random samples here? Children and adults? So I have two independent samples stated, and that is sufficient.
Could we, like how we can do random stated, could we do independent stated?
Mm-hmm.
Okay.
Mm-hmm. But usually with random, since this is independent, is different than our 10% independent. So just be careful that you don't use that as your 10%. You know what I mean? So then there's the 10% condition. This is dealing with the probability needed for standard deviations. So we check our sample sizes. Okay, well, what was the sample size for the adults? Okay, 100. So is 100 less than 10% of all adults? I think that's a safe bet, right? And 80 children? Is 80 less than 10% of children? I think so. Depends on the country. Did you say that? All right, large counts or normality. This is the booger, right? So now large counts is where we have to go back and use that pooled p-value, right? So I'm just going to do my work up here. We said with the adults, there was 34 out of 100. And the kids, 75% of 80 is 60. So when I add those up, I get 94 out of 180. Put that in my calculator, it comes to 0.52. Now, this is the value I need to use in my large counts test. So when I do my adults, it's going to be 100 times 0.52, 100 times the complement, 0.48, which is pretty simple. Those are easy math to do. Okay, those pass. And then I do the children, which the sample was an 80. That gives me 42, which is greater than or equal to 10. And then 80 times the complement of that would be 38. Okay, so they both pass, so we're good with that. Just want to make sure you catch that. This is where we use that pooled value, okay? That's where we need that pooled value work to show up in our work. So as we continue on, so now we've checked our conditions. Now we do the do step. So we need to show our curve. We know that this is a, what did we say, a left tilt curve. All right, and we said that x1, our work, is going to be 34, n1 is 100, or I guess a, we should use a, be consistent. xc was 60, and nc was 80. And then we're going to use our calculator here to find our z-score and our p-value, all right? Okay, so stat number 6. Now the nice thing about your calculators, let's say that you didn't do the math and you weren't sure what x1 and n1 are, okay? See, I couldn't do 34% times 100. I could put in 0.34 times 100 and it will generate it for me. You can't see it, but it made it a whole number. So this was 100. So like this one was a little different, right? 0.75 times 80. And it will calculate it for you. So maybe you do this before you do your PC. Maybe you need to do that. I don't know. But this is 80. All right. And we want less than, right? And then calculate. And there's our values. So all right, look, that z-score is a negative 5.47. That's really far out there, isn't it? Really far out there. So what's our p-value? Pretty much a 0, right? Pretty much a 0. And that's what we need to know. So we're going to transfer our z-score and our p-value back to our paper. All right, we said z was negative 5 point, what was it? 472? Okay, and p was approximately 0. Okay. So nice, right? Then we do a conclusion. Since 0 is less than 0.05, what are we going to do here? We reject the null. Do we have convincing evidence of the alternative? Yep. We have convincing evidence that, I'm going to go back to my parameter at the very beginning of the state, the true difference in proportions of adults and children who sleep with a comfort object that true difference is less than 0. So, a lot of the steps are very repetitive from chapter 9, aren't they? Very, very